Okay, so this is going to be your lesson 16 instructional video, and give me a second, let me change mics because it's going to be... Okay, so hopefully you can hear me better now. Anyway, this is going to be your lesson 16 instructional video, and what we're going to be covering is combinations and binomial expansion. So what we're going to have to learn about before that is factorials, which are a huge part of combinations, and then we'll see what we're going to be using those for, and that's going to lead us into what is sigma notation, and that's by extension going to be applied in the binomial expansion theorem. Okay, so a whole lot of new notation being thrown at you, but nothing too crazy. Right, so first let's start with what are factorials. So if I say n factorial, okay, I'm saying n times n minus 1 times n minus 2 times n minus 3, on and on and on and on and on. So that probably doesn't make a whole lot of sense without seeing numbers being put to it, so we've got plenty of examples to look at. So here, this example 1, I've got 3 factorial. All this means is 3 times 2 times 1, right? So 3 times 2 is 6, 6 times 1 is still 6. So 3 factorial is equal to 6. Next example, 4 factorial. That's equal to 4 times 3 times 2 times 1. 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is 24. So 4 factorial is 24. Next example, and this one's going to be hard to wrap your head around it, okay? And I'm going to leave you to do some research on your own as extra credit. So if you want to email this to me or Miss Roundtree, y is 0 factorial always equal to simply 1. So 0 factorial equals 1. I want you to do some research and try to explain why, okay? So for extra credit, email that proposed explanation or proof or whatever you want to call it to either me or Miss Roundtree. Okay, so anytime you see 0 factorial, it's equal to 1. That's basically all you need to take from that there on number 3. Okay, number 4, now we're going to look at some rational expressions involving factorials. So 7 factorial over 5 factorial. So something interesting here is going to happen. So 7 factorial, right, we can say that 7 factorial is equal to 7 times 6 times 5. And we can stop there and say that it's equal to 7 times 6 times 5 factorial, right? Why would that be useful? Well, if we're doing this by hand, which we're going to have to because, you know, none of us have fancy calculators that can do this. So if we're going to do this by hand, we need to take every shortcut that we can. So 7 times 6 times 5 factorial, well, what does that mean we can do? Well, here in the denominator, we also have 5 factorial. We can just cancel those out by a factor of 5 factorial. Okay, so that leaves us with just 7 times 6, which is 42. So 7 factorial over 5 factorial simply equals 42. Okay, and last example that we're going to look at. So same idea here. 10 factorial over 7 factorial. Well, let's shorten this down and use our same little shortcut that we used a second ago. So 10 times 9 times 8 times 7 factorial over 7 factorial. Those will cancel. 10 times 9 is 90. 90 times 8 is 720. 10 factorial over 7 factorial is 720. So now that we're familiar with what factorials are, let's start exploring what we can even use them for. And the main thing that you're going to see them in is probability and statistics, okay, the branch of mathematics that I absolutely despise. But nonetheless, it is a very important branch of math, okay, especially in the physical sciences, chemistry, physics, even biology. Probability is super, and statistics, super prevalent there. So got to get used to it. Okay, so first let's explore what combinations are. So combinations in math statistics or probability, they're collections of items which are chosen without regard to order. Okay, so we have special notation for that right here, right? And what this reads as is n choose k. right? So N is the number of items, K is what we're choosing from that total, right? So N is the total, right? So N is the total, and K is what we're choosing from the total. Oops, can't spell. Okay, so to further illustrate what it is I'm talking about, here we have an example. Okay, so we're here. So Deadpool's got 8 weapons, 2 swords and 6 different firearms or guns. Okay, so from these 8 weapons, he can carry only 4 at a time since he always forgets his bag full of weapons. Okay, and if you've seen either of the movies, he does that all the time. Anyway, so example 1. How many different weapon combinations are possible for Deadpool, assuming he doesn't always carry his swords, right? So what that would mean is that he's got 8 weapons, and he wants to choose only 4, okay? So from 8 of his weapons, the 2 swords and the 6 firearms that he has, he can only choose 4 at any given time, because that's all he can carry. So, that said, what we're going to end up with using this notation is we're going to say 8 choose 4. And another way to write that would be this way, 8 choose 4. Stacked like that in parentheses. They mean the same thing. Okay, and what it amounts to, mathematically speaking, right, N choose K, or 8 choose 4, is going to be equal to N factorial over K factorial times N minus K factorial. So 8 minus 4 factorial, which would just be 4 factorial, because 8 minus 4 is 4. Okay, so we're going to use our little shortcut we saw earlier. So 8 times 7 times 6 times 5 times 4 factorial. All of this over 4 factorial. Those are going to cancel out. Okay, so, oh, and I forgot there's a second 4 factorial here. What's wrong with me? So only one of those canceled out. So we've got 8 times 7 times 6 times 5 over 4 times 3 times 2 times 1. Okay, well, this 3 times 2 is equal to the 6, right? So now I've just got 8 times 7 times 5. Well, I can cancel a factor of 4 out of the 8 and the 4. So what that's going to leave me with is 2 times 7 times 5 over, and then over here I'm left with just 1. So that's going to be 14 times 5, so 50 plus 20. That's going to be just 70. Okay, so there's 70 possible combinations of weapons that Deadpool's going to be able to carry. Okay, now let's look at a different perspective of this scenario. So, how many different weapon combinations are possible for Deadpool, assuming that he does always carry his 2 swords? And again, if you ever read the comics or watch the movies, he does actually always have his 2 swords. So, what does that mean? Well, that means now he only has these 6 firearms to choose from, so N is now 6, right? And we're only going to be able to choose, so it needs to add up to 4. He can only ever carry 4 at a time. So it's going to be 6 still choose 4. And actually, it'll be 6 choose 2, right? Because if he's already using his 2 swords, right, K is going to be equal to 2 now. Okay, because 2 swords took up 2 of those spots for the 4, right? So it's going to be 6 firearms, choose 2. So he's only going to be able to choose 2 more weapons that are firearms. So 6 choose 2, 6 factorial over 2 factorial times 4 factorial, right? Because 6 minus 4 is 2. And we're going to have 6 times 5 times 4 factorial. All of that over 2 factorial times 4 factorial. 4 factorials cancel. I'm going to have 30 over 2 factorial, which is just 2 times 1 or 2. And I'm left with 15. Okay, so if he's always going to carry his 2 swords, there's only 15 combinations of firearms that he's going to be able to carry with him in those 2 other weapon slots. Okay, so now let's go a little further down the rabbit hole. Okay, so it seems like we're going all over the place, but this is all leading towards something, I promise. Okay, so combinations has its benefits, and you really need to understand it because you're going to see combinations all the time later on. You're also going to see this a lot later on, sigma notation. Okay, so what on earth does this mean? So I've got this big E looking thing with an n, k equals 0, n times x to the k, right? So what this means is, this is called a sum, right? So another name for sigma notation is summation notation. Okay, summation notation or sigma notation. Now, this is important because you're going to have instances where things are just being added constantly and constantly and constantly. Okay, and especially when you get into Cal 2, you're going to see a lot of these. They're called infinite series, and you're going to see a bunch of them. Anyway, so the way I would write this, right? So this is where I start, and I'm putting this very, very basically. This is where I start. This is where I end. Okay, so I'm going to start at k equals 0, and we're going to go ahead and assume that k is on n, meaning it's a natural number, 0, 1, 2, 3, on and on and on. Okay, so what we're going to do, so n times x to the k power. So I would go ahead and say n times x to the 0 plus n times x to the, to the first, right? We're going 0, 1, 2, on and on and on, plus n times x to the second, plus n times x to the third, plus n, and I'm going to go ahead and go into the ellipses here. So it just goes on and on and on forever, n times x to the k, right? So it just goes on. Okay, so let's look at an actual concrete example that has numbers for us. Okay, so we're looking at this guy here. So now I have a number for n, so that's going to be our end, right? And my start, or my initial value of k is right here, and this is going to be my start at 0. And I'm saying n, so n is right here. So I'm going to say 4 times 2 to the k. All right? So the way this is going to work, I'm going to start at 0 and end at 4. So I'm going to say 4 times 2 to the k plus 4 times 2 to the k plus 4 times 2 to the k. And I'm just going to keep on going. Okay, so I've reached my ending point, right? It's 4. So that means I'm going to go ahead and stop. Okay, so this was my start right here, 2 to the 0, and there is my end, 2 to the 4th. Okay, and what I would do to get my final answer, if you haven't guessed, is just simplify and add this all together. Right, so 4 times 2 to the 0, well, that's just going to be 4 times 1, because anything to the 0 is 1, so that's just going to be 4. And then we're going to have 4 times 2 to the first, so plus 8. 4 times 2 to the second, so that'd be plus 16. Then I'm going to have 4 times, so 2 to the third would be 8, so 4 times 8 is 32. Then 4 times 16, which would be 64. Okay, and then I would just add this all together. So 12, that's going to be 28, that's going to be 60, that's going to be 124. Okay, so my answer to this sum would be 124. And it's much shorter to just write that using summation notation or sigma notation than it is to actually just write this all written out. Okay, so let's look at one more example, and then we'll get to the whole point of understanding this. So here's my end. So my n is k, or my n is 3. What's the matter with me? And then k equals 0, negative n to the k. And this is going to form something interesting. Now, we know what n is. So n is 3. So I'm going to say, and actually, here, let me back up, because there's a typo in here that I thought I fixed, but I guess I didn't save it. So I was supposed to have put this in parentheses. Always nice when you find little Easter eggs like that, isn't it? Anyway, so let's go ahead and fix this. So This is going to be 3, so this is going to be negative 3, all raised to the k power, and our initial k is 0. Okay, and our stopping point is at 3. So we're going to have 4 terms. So we're going to have negative 3 to the 0 plus negative 3, I should do this in parentheses, negative 3 to the first plus negative 3 to the second plus negative 3 to the third. Okay, and again, here's my start at 0 and my stop at 3. Right, so now I'm just simplifying. So this is going to be 1, and then we're going to have minus 3, and then we're going to have plus 9, right? Because negative 3 squared, that's negative 3 times negative 3, so positive 9. Then we have negative 3 to the third power, and this is important. So this is odd, so that means I'm going to be negative, right? If you have a negative number raised to an odd power, your answer is going to be negative. Same over here. If you have a negative number being raised to an even power, then your answer is always going to be positive, which is why we had a plus 9. So this is going to be minus 27 here. So 1 minus 3, negative 2, plus 9, 7, and minus 27, negative 20. So my sum here would be negative 20. Okay, so now that we more or less understand how sigma notation works, let's start applying it in algebra. Okay, so this guy right here, x plus 1 to the third power. So we could FOIL this out, right? And you can already look at this, and you're probably just like, oh God. And you'd be right to do so. It's going to suck. Now, what we can do is use combinations and sigma notation to do this. Okay, and the reason for that is because, and I'm not going to go too deep into it because I'm probably already blowing your minds with all this new notation. Okay, but the reason for that is if we have a binomial, namely a plus b, and it's all being raised to the nth power, it can be expanded using a combination and sigma notation. Namely, so n is going to be our stop. Okay, we're going to have our initial k of 0, and we're going to go ahead and say that, so a is going to be raised to the n minus k, and actually I'm getting ahead of myself. First, we have the combination, so we're going to say n choose k. Okay, then we have a to the n minus k times b to the k. Right? So what that's going to look like, well, that's why there's 3 examples on here. Okay, so looking at the abstract, obviously that's horrifying. Let's go ahead and look at it with real numbers, and it'll make a lot more sense. It's actually quite an easy pattern to follow for the most part if you stay organized. Okay, so how would I express this guy using sigma notation? So sigma, n is 3, initial is 0, and we're going to do n choose k, right? And a, in this case, so a plus b all raised to the n. So a in this case is x raised to the n minus k times b to the k. And we're going to expand this out the same way as we were doing here with this sigma notation in these earlier examples. Okay, so we're going to write out everything. So 3 choose 0, right, because that's our start. So 3 choose 0 times x to the 3 minus 0, and that times 1 to the 0, plus 3 choose 1 times x to the 3 minus 1, times 1 to the first power, plus 3 choose 2 now, times x to the 3 minus 2, times 1 to the second. And our last term, 3 choose 3, times x to the 3 minus 3, times 1 to the third. Okay, so again, staying organized here is key. all right? So 3 choose 0. Okay, so what are we going to have for that? So 3 choose 0. That's equal to 3 factorial over 0 factorial times 3 minus 0 factorial. So that would just be 3 factorial again. 3 factorials will cancel. We're left with 1 over 0 factorial, which is just 1 over 1, which is 1. So I have 1 times x to the third power times 1. So 1 times x to the third power times 1 to the 0, which is 1. So our first term is simply x to the third. Okay, well then, next term, I've got 3 choose 1. That's 3 factorial again, over 1 factorial times 2 factorial, because that's 3 minus 1 is 2. Okay, so that's going to be 3 times 2 times 1 over 1 times 2 times 1. And that's going to be 6 over 2, which is just 3. Okay, so I'm going to have 3 times x squared. So I'm going to have plus 3 times x squared times 1 to the first power, which is just 1. Okay, over here. So now we're getting in the groove of things. So 3 choose 2. Okay, so 3 choose 2. That's going to be 3 factorial over 2 factorial times 3 minus 2 factorial, which is 1 factorial. So that's just going to be 6 over 2, which is 3 again. And you'll notice a pattern here when you see, so 3 choose 1, 3 choose 2. You'll notice that when you do the practice as well. Okay, I'll save that. So anyway, so 3 choose 2 is 3. Okay, so times x to the first power times 1 to the second power. So that's just going to be plus 3x. And then here, 3 choose 3. Okay, so that's just going to be 3 factorial over 3 factorial, 0 factorial. Those cancel. 1 over 0 factorial, well, that looks familiar, right? That's just going to be 1. So our last term is 1. Okay, so this seems daunting at first, but trust me, for the larger binomials, right? So if this was raised to the 6th power, the 7th power, whatever, it's so much easier to do this binomial expansion than it is to do anything else. Okay, so let's go ahead and look at a couple more examples that are quite a bit uglier than this. Okay, so this one wasn't so bad. The next one is going to be a little bit ugly, not going to lie. Okay, so next one we're looking at, and I'll do this one in blue. That's number 1. Okay, so our actual sigma notation, we're going to say n is 4. Obviously, initial is 0. Okay, n choose k. Oops, not 0. What's wrong with me? Okay, our a is x. So x to the n minus k times b to the k. Right, so from here, we're just writing it all out now. So 4 choose 0 times x to the 4 minus 0 times 5 to the 0 plus 4 choose 1 times x to the 4 minus 1 times 5 to the first plus 4 choose 2. And you can see how this pattern is going. Times x to the 4 minus 2 times 5 to the second plus 4 choose 3. Give myself some room. 4 choose 3, x to the 4 minus 3 times 5 to the third. And our last term, 4 choose 4 times x to the 4 minus 4 times 5 to the fourth. Right, so 4 choose 0. Okay, we remember from the last example, right? When we have something choose 0, our answer is always going to be 1. So for this term, my coefficient is 1 times x to the 4th times 5 to the 0, which is also 1. So that's just going to be x to the 4th for our first term. And then plus, so 4 choose 1. So this is another pattern that we're going to notice. So 4 choose 1 is going to end up being just 4, and I'll show you why. So 4 factorial over 1 factorial times 4 minus 1 factorial, so that'd be 3 factorial. That's going to end up being 4 times 3 factorial over 1 factorial times 3 factorial. Those will cancel. That leaves me with just 4 over 1 factorial, which is 4 over 1, which is just 4. Okay, so 4 choose 1, that's just 4. Okay, so that's going to be 4x to the third times 5. So I can go ahead and simplify that. 4 times 5. Go ahead and combine those like terms. So I can say 20x cubed. Okay, so that term is done. Now we're on to the next one. 4 choose 2. 4 choose 2 is going to look like this. So 4 factorial, 2 factorial, and 2 factorial again. So that's going to be 4 times 3, which is 12, times 2 factorial. Cancel 1 top and bottom. That's going to be 12 over 2 factorial, which is 12 over 2, which is 6. So that's going to be 6 for 4 choose 2 times 25. And 6 times 25 is going to give me 150 times x squared, so plus 150 x squared. Okay, then we're going to move on to this term. So 4 choose 3, and you're going to notice a pattern here. So I'm going to do it next to 4 choose 1. So 4 choose 3, that's going to be equal to 4 factorial over 3 factorial times 1 factorial. Okay, and we're going to have 4 times 3 factorial over 3 factorial times 1 factorial. 3 factorials cancel. Holy dog crap. We end up with 4. So 4 choose 1, whoops. 4 choose 1 ends up being identical to 4 choose 3. Okay, and you saw an example of that earlier. Okay, so my term here is going to be 4 also, here with the 4 choose 3. So that's 4, and then 5 to the third power. So that is going to be 125. So 125 times 4, that's going to be 500. So plus 500 x to the first power, right? And our last term, 4 choose 4. Well, that's just going to be 1, because we're going to end up with 4 factorial over 4 factorial times 0 factorial. Cancel, cancel, 1. Okay, so there's some identities we'll notice there. And x to the 4 minus 4, that'd be x to the 0. So 1 times 5 to the 4th. It's just going to leave me with 625. Okay, so this would be my binomial expansion of x plus 5 to the 4th power. Again, that would suck really bad to FOIL that out. It'd be so easy to make a mistake. And it's so much simpler to just use summation this way, to use the binomial expansion theorem. Okay, so again, work smart, not hard where you can. Okay, so a little bit different here. So now my a is 2x, right? So I'm going to go ahead and say, so n is 5, k is going to be 0, and we're going to say n choose k, and this time a is 2x. So it's going to be 2x to the n minus k, not just x, right? And then times, and this is also different. B is -1 now. So we have to say -1 to the k. Okay, so this one's going to work out in an alternating fashion, right? And you'll see what I mean here in a second. So 5 choose 0 times 2x to the 5 minus 0, so just to the 5th, times -1 to the 0, plus 5 choose 1, times 2x to the 4th, times -1 to the first power, plus 5 choose 2, times 2x to the third power, and that's times -1 squared, plus 5 choose 3 times, times 2x to the second times negative 1 to the third. And this is where the even and odd exponents are really going to play in. Plus 5 choose 4 times 2x to the first power, negative 1 to the fourth, and I ran out of room, but that's not that big a deal. Plus 5 choose 5 times 2x to the 0 times negative 1 to the fifth, right? So start from the drawing board, start with our first term. So 5 choose 0, we already know that's going to be 1. Right? Anytime you have n choose 0, we should have learned this by now, that's going to be 1. Okay, anytime you have n choose 1, that's just going to be equal to whatever n is. So for example, on this next one, when we have 5 choose 1, that's just going to be equal to 5. Okay, so that's two little identities there. All right. So this first term, that's just going to be 1 times 2x to the fifth. Okay, so 2 to the fifth, that's going to be 32. So I've got 32x to the fifth power times negative 1 to the 0, which is just 1. So 32x to the fifth power, that's my first term. 5 choose 1, that's going to be 5 times 2x to the fourth. So 2 to the fourth is just 16. So I'm going to have 16 times 5, so that's 80. And this 80 here is going to be negative because of this negative 1 to the first power. So it's going to be minus 80 times x to the fourth power. Okay, and then we're going to have, so 5 choose 2, we're going to have to actually write that one out. So 5 choose 2. 5 factorial over 2 factorial times 3 factorial. 5 times 4 times 3 factorial. Those will cancel out. We'll end up with 20 over 2, which is 10. So 5 choose 2 is 10. So we're going to say plus 10, right? Because this negative 1 is to an even power. And this is going to be 8x to the third. So 8x to the third times 10, that's going to give me 80x to the third. Okay, next term. 5 choose 3. Okay, so 5 choose 3 is going to end up being equal to 5 choose 2, and I'll show you why here in a second. So 5 choose 3 is going to be 5 factorial over 3 factorial, 2 factorial. Does this look familiar to this? Obviously. So this is going to give me the same thing, 10. Okay, so 5 choose 3 is going to be 10. 10 times 2x squared, so that's going to be 4x squared times 10, so that's 40. Right, so we're going to have minus 40x squared. It's going to be minus because this is an even number for the negative 1. Okay, so there's some patterns we're catching on to. Okay, the 5 choose 4. The 5 choose 4 is going to be the same as the 5 choose 1, right? So if I go ahead and write it out, 5 choose 4, that's going to be equal to 5 factorial over 4 factorial times 1 factorial. And that's just going to be equal to 5 times 4 factorial. And you get the idea. It's going to cancel out with the 1 here on the bottom, leaving me with just 1 factorial. So 5 over 1 factorial, that's just going to leave you with 5. Okay, so 5 choose 1, 5 choose 4, they end up being the same thing. Okay, so that's just going to be 5, and then times 2x, so 10x, and then we have an even power, so it's positive, so it's just going to be 10x plus 10x. And our last term, 5 choose 5. So n choose n also always equals 1. So 5 choose 5 is going to be 1. 2x to the 0, 1. So 1 times 1. Now, this is an this is an odd power, so it's going to be minus. So I'm going to have 1 times negative 1, so minus 1. So my answer here is given by the binomial expansion. And again, I challenge you to FOIL that out. That's really going to suck. This looks crazy, but this is so much simpler. Okay, so that covers everything in the lesson. Obviously, like before, if you have any questions, let me know. Otherwise, goodbye.